Okay, today we're going to be looking at diffraction. Previously we defined the properties that make a wave, and one of those properties was the property of diffraction. So what is diffraction? So diffraction is the property of when a wave passes around an obstacle. For example, if you had this is a mast that's kind of letting off a radio signal, and here we have a hill. And the mast, here's your wavefronts coming out of the mast, and they hit this hill, and they don't go through the hill. They're blocked by the hill. And what will happen is, as the wavefront passes the hill, it kind of bends round it like this. And this is, well, firstly, that you will get some interference if you're down here. It's not bent round here far enough. So if you are listening to the radio in the car driving through a mountainous region, you'll get disturbances in your radio signal, for example. But this also explains why radio signals can be picked up across the country. They can bend this kind of bending effect, that this diffraction of the wave enables the signal to be transmitted even where there's high buildings, or in this case a hill. So the spreading is called diffraction. Now this is a long wavelength. If we have a short wavelength, the effect of spreading is, the diffraction is going to be not as much. So this is our shorter wavelength. So we do get the diffraction happening, but it's not going to happen to the same degree as with a long wavelength wave. So this is our short wavelength. And this has implications on radio transmissions. That's why some radio transmissions are medium wave and some are long wave, if you look at the settings on your radio. And it will affect how well those waves travel over a long distance, and how they're affected when they come to more hilly mountainous areas or through cities where there's lots of high buildings. Now you can see this effect if you were to look in a ripple tank, for example, or if you're on the beach and the waves come in and you see a big boulder, the waves will diffract round the boulder as they pass through. Now to be able to investigate diffraction, it's important to be able, so when we're investigating, oops, that's terrible, investigating diffraction, what we need is to do so properly. We need coherent wavefronts. And we want two of these. So to make them coherent, we would have a single light source. So here's our light source, and it'll come out of our light source here. But then to make this a coherent to get two wavefronts together to see how diffraction, how the two waves as they undergo diffraction, how they interact with each other, we would pass this wavelength, this wavefront from the single light source through two gaps. So we'll call this S1 and S2. So these are slit 1 and slit 2. And then we will have a screen over here to observe what happens. This method of observing diffraction led to a very famous experiment called the double slit experiment. And it was done by an English physicist in the early 19th century called Thomas Young. And this is one of these really groundbreaking experiments that has happened. So the wavefronts will spread out like this. And as you can see, as they spread out, they are going to interact with each other. And just like what we saw in our last lesson, they will create this wave pattern where you will have down the set. I'm going to get some different colours because it's getting messy. So this is our central line here. We will have a maximum, and then we'll have a minimum, maximum, minimum, maximum, so on and so forth. And here we get our interference pattern. And a neater picture of it is here, where you've got the interference pattern, and the most central ones will be the most give the strongest result, with them getting fainter as they head out. Today, the double slit experiment is carried out by lasers. So today we use lasers to give a coherent wavefront. And if we look, I've got, here is an example of what you would get with the differentiation pattern with a laser light. So you get this bright central maximum, and they get fainter as they go out. Now it's possible to calculate the distance between the slits based on the positions of these maximum and minimums. So let's draw, here's our slit here, here's S1 and here's S2. And the distance between them, we're going to call this D. Now we have the screen on which the interference pattern will be observed at a far enough distance away from the slits so that the beams of light are coming out parallel to each other. Now if this is the central point, I'm going to just draw a dotted line. Now let's say here is our maximum. So we've got the light coming from here, oh dear, let's redraw that. Was it going to meet the right place? And from here. Now, the difference in these two rays coming out here is x, so right angles, and this is x. So x is the path difference of the two waves. And we know from our last example, this is a maximum here, this is also a maximum here, that when x, the path difference, is at a maximum, it must be some integer number, whole number, times the wavelength to give the path difference. So this is what the first maximum to be m1. Now this angle here is theta. Now because the rays of light coming out, the beams coming out from slit 1 and slit 2 are parallel to each other, this, and this is the central point, it would mean this angle here is also theta. And what this gives us is d, the distance between the slits, sine theta is equal to the path difference. And if we have, let's just bring this one back up here. Oh, no, I won't do that one up. So here's our maximum minimums. So this central one would be m equals 0, and then you'd have m1, m2, and so on and so forth. And then the minimums are at, would be m equals a half, m equals 1.5 distance away. So that's what we did it in the last lesson, if you want to review that at all. Now, this equation holds true, oops, wrong thing, I want to get rid of that, for multiple slits too. So a larger number of slits, so if you've got, let's put this up, so a larger number of slits leads to the maximum and minimum being more defined. So what we can do is we can actually have a grating. So you can bring in your beam of monochromatic light. So monochromatic, this is monochromatic. So monochromatic, mono means single, chromatic is colour. So this is basically coherent light, single wavelength. Oops. So like from a laser is the best way of getting some monochromatic light. So, dearie me, it's not very neat at all. So we've got this parallel beam of monochromatic light, and then it's going to hit what we would call a diffraction grating. So diffraction grating is made from glass, and they're specially fabricated, and there would be like opaque glass with etched into it these very close slits, and you'd have a number of different slits down here. And then what then happens, you have your screen. It's meant to look like it's parallel. And you'd have your interference pattern coming out here onto this screen. You can also use a white light source on a diffraction grating, and because let's look at our equation quickly. So our equation still stands: d sine theta equal to m lambda, where lambda is the wavelength and m is the position of the maximums. If you have white light, the lambda is going to be variable because white light contains a multitude of different wavelengths. It's no longer monochromatic. And what this equation shows us, that there's going to be the positions of your maximum and minimums are going to be affected by lambda, because different wavefronts are going to have a different path difference depending on the wavelength of light. And if you were to pass a white light through our diffraction grating, you would get something like this, where you've got up on the top is some green monochromatic light from a laser, but down here you've got this rather beautiful interference pattern. The central maximum m equals 0 is white light, because when it comes in here it all gets concentrated on that single point, but these further out patterns, the light gets split up. Similarly, if you were to put the light through a prism, so a diffraction grating works in a very similar way to a prism, that it can break up white light into its constituent wavelengths and create these beautiful effects. If you have a CD or a DVD, let's talk about, let me clear this just now. Let's talk about interferometers. So, if you have a surface that on a microscopic level has grooves like this can act like a diffraction grating, and will break up the wavelength of white light, but it also will create, if you were to shine a laser on this surface, you would get an interference pattern. So CDs, DVDs have microscopic grooves, and these act like diffraction gratings. Now, if you get a DVD, if you've got a laser pen and you were to shine the laser pen on the top of the DVD, you would end up having created on your wall or whatever one of these interference patterns, very much like this one. It'd be probably much more spread out actually. But this then brings some really important applications. So if you wanted, you can use this property to create an interferometer. So an interferometer uses different wavelengths of electromagnetic waves to calculate the depth of an object. So you can shine your light or your wave onto the surface, and the pattern that's produced can be detected, and you can then calculate how deep these grooves are on the subject, on the surface. Now this is really quite important, because you can, if say you wanted to create a really detailed image of the surface of something, you're able to do it using interferometers, and it has applications, say, in space physics, where you want to make mirrors that are highly precise and very perfectly polished and flat. So you need to be able to see if there's any defects on those mirrors. You can use an interferometer. as well as other types of industrial materials where you want to check for cracks, or if you want to check for any defects, you can use these interferometers for that purpose. Now let's look at an example on how to do some maths with our equation for diffraction. So a grating is placed in front of a laser emitting light with a wavelength of lambda equal to 635 nanometers. The third maximum occurs at an angle 27 degrees to the center of the grating. Calculate the distance between the slits. So we've got our equation, d sine theta equals m lambda. D is what we want, and we've got sine of 27. We know it's the third maximum, so third maximum, and we know the wavelength is 635, and it's times 10 to the minus 9. Remember, nano is to the minus 9. So rearranging that, we'll get D as 4.1961 times 10 to the minus 6 meters. And if it's minus 6, we would write that as 4.2 micrometers. So I hope that helps.